Hello everyone. In this video, we will be discussing circular motion as part of the IB syllabus. So as always, this video will be split into two parts. First part containing basic information or semi-basic information about different scenarios where circular motion is involved. And the second scenario is IB questions. So this part of the video, I will be doing two different IB questions, which are part of the exams from different years, and therefore we'll be going through a detailed analysis as to how to solve this question or how the exam style question is structured. And as always, timestamps will be provided in the description as to which section we're doing within the video. So I've also provided formulas on the right side over here. So these are formulas that are provided within the formula booklet. So there are certain formulas that do not have to be memorized, and these are the three formulas part of the circular motion. So let's begin with the first scenario. The first scenario includes of a circle and a car, or any object traveling in the circular motion horizontally. So we have the car, and as I've mentioned before, this is not the absolute basics of a circular motion concept. So you are to know that centripetal force acts towards the center of the circle, and you're also to know that velocity vector is tangential to the circle. So this is knowledge that you have to have prior to watching this video. So what I'm doing in this video is to see how the following circular motion is related with the scenario in hand. In this case, a car traveling in a circular motion. We may be asked to find the velocity that this car travels to maintain the circle. And so we have to find that, and we're probably provided with radius, which let's assume is 50 meters. And another piece of information we will be provided is with the coefficient of dynamic friction, which may be something like 0.8. So using this information, we have to find what velocity must this car travel so it doesn't go off track. As I've mentioned before, centripetal acceleration goes towards the center. The car traveling has friction towards the side, meaning Fs is actually equal to Fcp. And Fs, as we know, is coefficient of dynamic friction multiplied by F normal, which Fcp we know as mv squared over r. Now, since the horizontal forces acting in the y direction is 0, mg is equal to Fn. So we can also go ahead and say that ud multiplied by mg is equal to mv squared over r. And through algebra, we know m's cancel, and we get ud multiplied by g equal to v squared divided by r. Now, reorientating this equation, we get v is equal to gr times ud. V is equal to square root of gr ud. And just like that, we can find out what velocity must it travel in order to maintain the circle. And that was the first scenario. Moving on to the second scenario, we have a little bit more of a complicated situation here. So we have a triangle, and we have an object traveling in a circular pattern. Say this angle is theta, and we have to deduce again what velocity must it travel. Forces that are particularly important towards determining the factor of centripetal force, Fg and F normal. Using these two, we can deduce what the centripetal acceleration would be. What we have to do is break down Fg or Fn into its components, where we know that F normal is equal to Wy, or Fgy, because this is the y direction and this is the x direction for Fg. So this is Fgx, this is Fgy. It's a little bit more less confusing, and say Fgy. And we know by previous knowledge on mechanics, Fn is equal to Fg times cos theta, because that is what Fgy is. And therefore, we know now F normal is Fg times cos theta. Now, if we rewrite this equation, we get Fg is equal to Fn divided by cos theta. And since there is no movement in the vertical direction, we know Fn equals to mg over cos theta. And that is what Fg is equal to. And therefore, we've determined that Fg is equal to mg over cos theta. Since Fgx is going towards the centripetal force, and since the center of circle is indeed here, this is the Fgx force over here. And therefore, we know Fgx is equal to Fcp, the centripetal force. And since Fg is equal to mg over cos theta, we know Fgx would be Fg sine theta. and that's equal to mv squared over r. And since fg is equal to mg over cos theta, we write mg over cos theta times sine theta equal to mv squared over r. We know that sine over cos is equal to tan. This means we get mg tan theta equal to mv squared over r. Again, masses cancel, and we get the following equation of g tan theta equal to v squared over r. And just like that, we can determine what velocity must travel just using gravity, angle, and radius. So we're going to go ahead and isolate v. So we get v is equal to square root g r tan theta. And that is the second situation with banked curves. Moving on to the third. Third situation includes of a string holding a ball spinning in the vertical direction. This means the ball will be here at one point, and then it will go over here, then it will go over here, and finally it'll end at the bottom. We're going to have to imagine that the ball goes in the circular motion vertically. Now let's break this down into different components. Let's first take this force, then this, and the final one fourth. The first force and the top part is that tension is acting this way. Because the string is pulling it from here, the tension will be acting this way. What also acts in this way is mg, which is also in this direction. And since centripetal force is the force acting towards the center, we can actually determine that FCP is equal to tension plus mg. That was the first situation of the string over here. Now let's have a look at the second situation. For the second situation, mg is down and tension is towards the center as again. This means for the second situation, we have FCP just equal to tension because that is the only force acting in towards the center. Now, let's take the third situation. mg down, tension up. So that means this would determine that the third one being FCP is equal to tension minus mg. And the final situation again is tension and mg. Again, it's the same scenario as with the second part, which is FCP is equal to T. As I said before, this is not the absolute basic, so this will be quite difficult to imagine if this is completely new as a circular motion. Moving on to the fourth situation, probably one of my favorite situations, is a car traveling a bridge. So for this information, we're going to ask what velocity is, as always, and all we're provided with is radius. And we have to determine at what velocity it must travel so the car doesn't just fly off the bridge, but make sure it stays in contact with the bridge as it goes down. The only force acting on this object is mg, and normal force of course, but the only force related towards the center of the circle is mg. This means that we get mg is equal to mv squared over r. That's it. Mass cancels. We get velocity squared is equal to gr, so velocity is equal to square root gr, and therefore we can determine what velocity it is. And that was the fourth situation.